The topic of this video is strain transformation. That's the method by which we take the strain components of an in-plane strain state and use those to compute what the strain components would be if we were considering a different coordinate system, but at that same material location. This video should teach you three primary things. First, to state how the strain transformation equations are obtained, to be able to use the strain transformation equations to calculate in-plane strain components with respect to some x prime, y prime coordinate system if you are given strain components at a point with respect to an xy coordinate system. So that means essentially we're taking the strain components in one coordinate system and computing what they would be in some rotated coordinate system. Now those first two learning outcomes are essentially the same as the learning outcomes from the previous video on stress transformation. Unfortunately, I forgot to include them in that video, but if you just swap out the word strain for stress, then these first two learning outcomes are the learning outcomes of the previous video. But this video has a third learning outcome, which is to compute the shear strain using normal strains measured by a strain rosette. So at the end of this presentation, I'll talk about what a strain rosette is and how we can use that to calculate shear strain. So like I said, strain transformation equations are used to obtain the strain components, normal strain in the x prime direction, normal strain in the y prime direction, and a shear strain with respect to an x prime, y prime coordinate system, given the strains that occur in what we'll define as our xy system. So just when we derived the stress transformation equations, we used the concept of equilibrium. Stress is a function of force, and whenever we're dealing with forces, equilibrium tends to be the guiding principle. Well, now we're talking about strain, and you should know that strain is a function of displacement or deformation. And when we're talking about displacements or deformations, that is typically associated with vectors and trigonometry, right? We break up our displacements into x and y components. And so if we have an object with, say, these initial coordinates, or not necessarily coordinates, but dimensions, say we have initially some small delta x and delta y, and that would mean that there would also be some initial delta x prime. So we have these three initial dimensions. And then let's say that we experience an extension in the x direction. That extension is given by the strain times the initial dimension in the x direction. That's this here is our how much the material is deforming in that direction. And we can break that up, for example, into components that are in the x prime direction, so that'd be this red arrow, and components that are in the y prime direction. So that would be this blue arrow. Similarly, if we have a displacement that is in the y direction, so this displacement here, we can once again break that up into x prime and y prime components. So we can say this red arrow is in the x prime direction, and the other vector that's needed to add to that to get the original y displacement vector is this component in the y prime direction. So if we have, like I'm saying, if we have extensions in either the x or the y direction, we can break those up into their x prime and y prime components. And similarly, if we're dealing with shear strain, so for example, if these two line elements that are initially perpendicular, see we have these two X and Y line elements. If we allow the vertical line element to come inward to this location, see we're coming in like this, that would be our gamma XY. Well, in doing so, this point here moves to here, and we can represent that by breaking that up into the components. And once again, this movement from this point to here carries with it a vector component in the x prime direction. You can see the full derivation. These figures come from section 10.2 of the Hibbeler textbook, and you can see the full derivation of the equations in that section. But essentially, you get the point here that we break up these components into deformation components that are in the x and y coordinate system into what their vector components would be in the x prime, y prime coordinate system. And then when you go through that full mathematical derivation, you end up with these equations. That your strain in the x prime direction in normal strain, your normal strain in the y prime direction, and your gamma, or your shear strain, can be expressed as functions of the x and y normal strains, as well as the shear strain in the xy coordinate system. Now note that these look identical to the stress transformation equations, derived in a completely separate way, but yet they turn out to be identical with one important exception. Anytime we had a normal stress, sigma x, we now have a normal strain, epsilon x. And anytime we had a normal strain, sigma y, we now have, normal stress, sigma y, we now have a normal strain, epsilon y. And anytime we had tau xy for a shear stress, we are now replacing that with gamma xy over 2. And you might see all these factors of 2 and think, well, I could just multiply everything by 2, but then we don't have our strains on the left-hand side isolated. But perhaps you could do that with this equation and get rid of these 2's, but we don't do that. For one reason is because we want to keep this term consistent, where it's the half of the distance between the two strains. That's a similar term here and here. And for another thing, this gamma over 2 actually has particular meaning in the field of engineering. We call engineering strain. So I want to conclude with an example. And by way of this example, I'm going to show you how to use the transformation equations to calculate shear strain using a strain rosette. So if we have a strain rosette, that means that we have 3 strain gauges all attached near one point location, and they're in a particular configuration. In this case, this is a 45-degree strain rosette, but there are other configurations that one could use. This is a very common one, however. And each of these strain gauges, so each of these green rectangles here, A, B, and C, they're going to be measuring the strain that occurs along their length. So they can measure the strain along the x-axis, the strain along the 45-degree angle, and then the strain along the y-axis. And when I say strain, I mean normal strain. Strain gauges are only capable of calculating normal strain, which means that our measurements from the strain gauge are epsilon A, epsilon B, and epsilon C, where epsilon A is the strain in the x direction, right? And epsilon C is the strain in the y direction. And I didn't write it down here, but epsilon B is the strain in that 45-degree direction. And we can give that direction a special name. We can call that our X prime direction, which means we're going to call this our Y prime direction. That's going to be a 45-degree angle there, right? So that we get a 90-degree. Okay, so now if we want to know the shear strain, we can obtain it by using the strain transformation equation, because we just agreed that the strain B is the normal strain in the X prime direction. Therefore, I can plug in the normal strains, strain A and strain C, here in this equation. So I can put strain A, I don't feel like doing that. So we can put strain A in these locations, strain C in these locations, and we know that the angle, whoops, can't read that. We know that the angle from X to X prime is what we're going to use as theta. So we have that. The only thing that we don't have is gamma, and that's what we want to solve for. So let's go ahead and fill all this information in. We agreed that the strain in the B direction is our strain, normal strain X prime, and we're going to add strain A plus strain C and divide by 2. Now for this second term here, notice that there's a cosine of 2 theta, and we agreed that theta is 45 degrees because that's the distance or the rotation between the x-axis and the x prime axis. And so 2 times theta is 90 degrees, and the cosine of 90 is 0. So this whole term is 0. So I don't need to fill in for that. But I do need that last term, gamma xy over 2. Now sine of 90 happens to be 1, so I can remove that. And if I want to know gamma xy, it turns out that I multiply everything by 2, and I get 2 strain B. I'm going to move strain A and strain C to the other side of the equation, and I get this equation that will always hold true. Anytime we're using a 45-degree strain rosette, we can always use this equation to get the shear strain. Even though we can't measure shear strain at that point, we can compute it. So hopefully you see how this equation works and how we used it to obtain the equation for strain rosettes. In a different scenario, different example, you could have been given values for strain, normal strain in the X and Y directions and the shear strain, and then you could have computed the strain in a different direction, or perhaps even be given displacements that allow you to compute the strain in these XY directions and then convert it to X prime direction.